Okay, let's get started. Thank you all for joining the seminar today. It's really our great pleasure to have Dr. Wei Gao from Caltech for today's seminar. I have known this work for a long time. It's a great pleasure. And Dr. Gao is a professor. By the way, can you guys hear me on the Zoom?
Yeah.
Okay, it's great. Dr. Gao is a professor of medical engineering and Heritage Medical Research Institute investigator at Caltech. He's our UC alumni. He got a PhD from UCSD and then postdoc training at UC Berkeley. He became a professor, I think last year, right? Or
2017.
2017
Oh, you mean
already.
full professor was
Yeah,
last year? Yes.
last year. So he's now the associate editor of Science Advance, MPJ, Flexible Electronics, Biosensors, Bioelectronics, and many other journals. And also he has already won a long list of awards, including NSF Quill Award, Sloan Research Fellowship, and there's many more. I wouldn't surprise one day there's a Nobel Prize on the award on the list. And he's really brilliant. He's tiny sighted researcher. Just give you guys an idea. His group just published 15, I counted this morning, 15 science and nature paper in this year. Remember that. So it's incredible. He's already a fellow from AIBME and Royal Science Society of Chemistry. His research interests including wearable biosensors, digital medicine, bioelectronics, flexible electronics, and 3D printing, micro, nano robots. And really, I think, as you guys can say today, we're not only learning his science and technology, but also we're learning how he present the science and technology, obviously, and hopefully we can publish a Nature Science paper also, right? Without further ado, and please join me and welcome Dr. Gao for the seminar.
Thank you very much for Sean for the kind invitation and introduction. It's wonderful for me to visit UC Irvine again after quite a few years. Actually, last visit probably 2018 already. So I would like to discuss our recent progress on body interface biosensors. A brief introduction about my lab. We are in a department called medical engineering, essentially biomedical engineering, but focused on translational research. So my lab had roughly 20 PhD, 20 postdocs, and they're both mostly focusing on developing different type of devices. These are some pictures you see. We develop different type of body interface device for health monitoring, for treatment. We also work on human-machine interfaces, as well as some we call micro nano robots that can go into the body for drug delivery. But today I will mainly discuss the research on body interface sensors. As we know, wearables, now is a digital era, and wearables can play a very important role in personalized healthcare because they can continuously collect data from our body and tell us what's going on and what's going wrong with our health. But if you look at all these commercially available health monitors, like Apple Watch or Fitbit or Oura Ring, now they can do a lot of things already, but they can only collect still very limited physical parameter information. The overall applications are still limited because such parameters can only tell us, our body vital signs. And we think a great challenge, which is also a great opportunity in this field, is how can we perform physiological monitoring not only at a physical level, but also at a biomolecular level. So especially non-invasively and continuously. Thinking about the biomolecular sensing, we know that there is CGM, continuous glucose monitor, which has changed the world for diabetes management already, right? But again, it is only limited to glucose monitoring and is still kind of invasive. So looking at non-invasive health monitoring, we are thinking, if we could develop this body interface biosensors, you can attach into different parts of the body. They can continuously and non-invasively analyze these alternative biofluids, not blood, but sweat, interstitial fluid, wound exudate, exhaled breath condensate, and GI fluid. Those are fluids you can non-invasively access. you can collect this large set of data from our daily activities. We could use this data for health monitoring, for disease diagnosis, and very importantly, this can give us early warning before we develop more severe health conditions for preventive care. And last but not least, the largest sets of biomolecular information are not previously accessible. If we couple this biochemical data collection with biophysical data collection, along with data analysis such as using AI or machine learning, you can imagine we can enable numerous fundamental and clinical investigations, especially to what we call a direction called biomarker discovery. Actually identify the correlation between the parameter you're monitoring with specific health data. So we have published a few review articles over the past years to discuss our vision toward this direction. If you have interest, you're welcome to read this more in details. The first fluid I want to talk, which we have been focusing on this for like 10 years already. So it's human sweat. We are essentially sweating all the time. I feel I'm sweating now already. So our sweat contains very rich biomolecular information, including a variety of electrolytes, metabolites, nutrients, actually over 300 proteins you can find from the skin sweat. And there are many different types of other molecules such as peptides, hormones, substances such as heavy metals and drugs come out through sweat gland. Imagine that, again, if we could collect data, right? We could get information non-invasively from our daily activity. Back to 10 years ago, while I was still a postdoc at UC Berkeley, in the case, we presented a wearable system that can real-time monitor metabolites such as glucose and lactate, electrolytes such as sodium and potassium, along with the temperature. So this system can do on-site signal conditioning, processing, and wireless transmission. So eventually all the data generated from skin can be sent to your phone wirelessly and displayed in a custom-developed cell phone app. You can real-time read the analytic concentration. When we do the human subject study, we recruit the subject to the lab, we give them our device, give them our phone, they can possibly run outside, they can bring back device, bring back phone. We can collect data. And eventually, this allows us to collect data from our daily activities. So this was published in 2016 and has been cited by over 5,000 times already. You can imagine that means many people are interested in this topic and many people have made tremendous progress in this field. But again, often we get a question, oh, where I can buy one. So we have to say, oh, it's not ready yet. Why? Because there are technical gaps. So back to 2017, when I joined my lab at Caltech, we thought about what are the challenges that can prevent us from just making like a accessible technology that can benefit people's health, right? We have been trying to address these challenges. From following slides, I will show you some challenges and how we try to address it. Firstly, a chemical sensor. It's not like a pacemaker. You can use one pacemaker for years. Chemical sensors, they are not stable. They cannot last long. Even CGM, people invest billions of dollars, I would say. You have to change the sensor every 2 weeks still. So ideally, most sensors cannot even work as long as a glucose sensor because that's probably the easiest sensor already. So ideally, we should make our sensor disposable at low cost so that you can change it every day or every week. If the cost is very low, we can use it. So we propose a few approaches. Firstly, laser engraving. It's a beautifully simple approach. Using CO2 laser, you can make this graphene structure on the surface of polyimide. You can burn the surface of plastic to cause localized carbonization in this case. And this graphene structure can have very good electrochemical performance, much better compared to commercially available glass carbon electrode, screen printed carbon electrode, or gold electrodes. So they can directly detect very low concentration biomarkers in human body fluid. If we control laser parameter properly, you can generate different type of graphene structure that can be very suitable for monitor body vital signs, such as temperature, respiration, or heart rate. Last but not least, if you use laser to cut through this medical adhesive or medical tapes, you can make microfluidics. So why we need microfluidics? Because we are doing sweat analysis. Always this question come out. What if new sweat come out, it mixed with old one? You don't get real-time information. And what if sweat evaporates? The chemical could build up, right? This can be a problem. But with microfluidic, we can address both problems. So now sweat gland is our pump, pumping water, pump sweat out of the skin. And when new sweat enter microfluidics, it will push away the old sweat. So fresh sweat will flow through top of a sensor, get real-time analysis. And because sensor is sitting inside this micro reservoir, in this case, we can say that have minimal influence from evaporation. Overall, physical sensor, chemical sensor, microfluidics can be prepared by using laser and plastics. You can imagine scalable and low cost. And actually, this is my first graduate student, Isabella. Because of this work, she got Forbes 30 under 30 in science. So we can do printing as well. Like in the office, we use inkjet printer to print different type of color documents. In this case, you are using commercial color inks, right? Instead of using that, we're thinking, can we use our own custom inks? Because different materials can be preferred, especially nanomaterial have unique property, right? If you want to detect certain compound, certain material may be preferred because their unique property. In this case, instead of using commercial color inks, we can make our own nanomaterial inks. The inks made of silver nanoparticle, carbon nanodots, gold nanoparticle, carbon nanotube, graphene oxides, and MOF, mixing, and encapsulation material. In this case, all you need to do is program from computer, then you can print different material at different location. Then you have this multimodal physical chemical sensing patch that can be used for human-machine interaction as well as for wearable sensing. So the third approach is 3D printing. 3D printing, we are very familiar already. It is very suitable for personalized prototyping, especially in the resource-limited environment. So we can make our own 3D printed inks in this case. You can print a biophysical sensor using this mixing ink, very high performance temperature and pressure sensing. And you can print a chemical sensor as well. But moreover, not only the electrode, but also functional films such as enzyme-trapped hydrogen. You can print microfluidics as well. Last but not least, you can print this even energy storage device such as micro supercapacitor. So overall, the disposable module of the sensor can be entirely printed. So I've showed you 3 approaches already for possibly scaling up manufacturing of this multimodal sensor patch. The next challenge is really, we always get this question, what if I don't have sweat? Right? Because when you do sweat analysis, we know that if we do vigorous exercise or get heat exposure, we always sweating a lot. But that's not daily routine, right? In a cold day or in a clinical setting or while you're sleeping, we don't sweat as much. So to make sure this technology can be broadly accessible, we need to address this challenge. How can we get a sweat at any time? Can we realize even 24/7 continuous monitoring? So with this in mind, we look at, what are the options? We found that there is a way you can induce sweat locally through a process called iontophoresis. Iontophoresis, you apply the FDA-approved device, actually, is a sweat test used in the cystic fibrosis diagnosis in the clinical setting. So you apply the small current between 2 FDA-approved electrodes. You deliver a drug called pilocarpine or carbaco, or could be even acetylcholine. This molecule, like acetylcholine, is neurotransmitter. They can bind to a sweat gland, trigger localized sweating. Why we are sweating? Because our body, when we experience heat, the sympathetic neuron near the nerve will secrete acetylcholine and bind to sweat gland like receptors to make us sweat. Now, instead of letting our body feel anything, you locally transdermally deliver this molecule to tell sweat gland to sweat. So using this approach, we can locally induce sweat at rest. The doctor will use this collector to collect sweat, send out this sweat to a lab to do chloride test, which is a gold standard for cystic fibrosis diagnosis. So inspired by this, we made our new generation with wearable sensor. It is a miniaturized patch with a small iontophoresis module, in this case, between these 2 electrodes. We are coating the electrode with a thin layer of hydrogel. The hydrogel is loaded with a drug called carbaco. Carbaco, if we apply a very tiny current, only 50 to 100 microampere current, way lower than commercial product, actually, so you don't even feel anything. Only for 5 minutes. And we deliver this molecule, they can stimulate the sweat gland. And this will make myself, with 5-minute stimulation, will make myself sweat for 2 days, only from this few sweat gland. And you don't even feel you are sweating. You don't feel anything at all. Unless you touch this area using your finger, you feel, there's more moisture. But that's enough for us already. By attaching a microfluidic sensor patch on the skin, now you can sample sweat, slowly and steadily secreted sweat. You see the black dye? Now, initially here, get pushed out to the outlet because sweat gland is the active pump. Keep pumping very steady and slow sweat out. Now another black dye get pushed out. So you can get a real-time now fresh sweat analysis using your sensor with a delay of only 1 to 2 minutes in this case. So this allows us to do a lot of clinical applications. So we now have the good sensor, have the way to induce sweat. Our lab also do the system integration to make sure we have the wireless system that you can readily apply to patients, to different subjects to collect reliable data, because data is the most important part for wearables. Yeah.
Is there a particular reason why the particular shape?
Not really. You will see that we have different shapes. There are some more optimal, but it will work. The most important part, you have two electrodes, you apply current and transdermally deliver this positive charge drug molecule below the skin. And by the way, I forgot to mention, this drug may sound scary, but the dose of the drug we are using, you always use it in eye drop. The dose is even lower than that, actually. It's an essential component of the most typical eye drop, actually. So we can package our device into different form factor, could be a patch, armband, or even a watch, or even a smart ring. You can wear this at different body parts to realize continuous, non-invasive, autonomous data collection. So I want to show you some applications. Firstly, disease diagnosis. So I mentioned earlier, cystic fibrosis is a genetic lung disease, actually. Clinically, the gold standard for cystic fibrosis diagnosis is based on sweat chloride, not blood chloride. So the doctor usually use this bulky, relatively bulky FDA-approved device to collect sweat from the newborn infants. That's why this procedure is safe. People use it on the infants already. So then need to wait days to get a result. So we work together with Stanford School of Medicine, Cystic Fibrosis Center. We applied our device on healthy people and on the patients. You see that instead of waiting for days, within 20-25 minutes, you can induce sweat locally and measure sweat sodium chloride on the skin already. And the patients, their sodium chloride level are very different compared to healthy people, much higher. Actually, the gold standard for adults diagnosis is based on chloride higher than 60. You can say that our device can be used for screening and diagnosing CF. You may argue, well, for disease diagnosis, I don't need a wearable sensor to monitor or diagnose every day, right? So it's true. That's why it's only just classical demonstration. But in reality, what our lab is focusing on, really, for most important part of the wearable is preventive care. Give people early warning before develop more severe health conditions. So we are looking at a lot of different type of metabolic disorders. One of the first one we're looking at is gout. Gout is the most common inflammatory arthritis, affecting tens of millions of people around the world. My brother has gout as well. It's a pity for gout patients if you like to eat red meat, drink beer, or eat shellfish, because too high purine intake will increase uric acid level in the body. And uric acid can crystallize near the joint, triggering tremendous pain, actually. So that's why uric acid is a well-established biomarker of gout. So we apply this on healthy people, male, female, you see that. We see after fasting, your sweat and blood uric acid are both very low. After dietary intake, they increase substantially. And in collaboration with the UCLA Clinical Nutrition, we actually recruited the patients with the gout as well. And for the patients with gout, their sweat and serum uric acid levels are much higher compared to healthy people. And if we track one subject for hours, and we can see that sweat and uric acid follows closely the serum one. That correlation, what we got between sweat and blood, is actually pretty high. It's 0.864 already. And this is just early demonstration. Now we can get even above 0.9 in this case, correlation with a further calibration mechanism. So uric acid is not only important for gout, it is also very important for cardiovascular disease, renal disease, or even for diabetes. But again, uric acid is only one of the biomarkers. So our body contains many important circulating metabolites and nutrients well beyond uric acid. For example, there are 9 essential amino acids. They are called essential amino acids because they are playing a vital role in our body function. We have also many different types of vitamin, lipids. This is all very important for our body function. But again, how we can monitor them? If we could track this biomarker level or nutrient level continuously, this is an important path to enable precision nutrition. Now NIH is emphasizing a lot. So, but again, monitor this biomarker or nutrients, they are not very straightforward often. I mean, ideally, if you could find enzyme like glucose oxidase, you could develop enzyme medical sensor like glucose sensor. That's the simplest. But again, for most of these targets, you don't have a suitable enzyme available for you to develop such sensors. That's why to address this problem, we are demonstrating molecule imprinted polymer, this MIP. This polymer, MIP polymer, works as artificial antibody. We can synthesize the polymer by mixing monomer cross-linker together with the target molecule. Now you can synthesize this MIP polymer, and after you remove the target molecule, MIP will maintain the shape. It will have a lot of cavities because originally the target molecule here, after you remove them, the MIP will have the cavities with the same shape and size as your target molecule. That's why they can recognize target back again, work as artificial antibody. Antibody recognize protein, one key mechanism is the shape recognition. So if you have this target recognition polymer already, if we coat this on the surface of our graphene electrode, now you could have a sensor. But again, you need to make sure you have measurable signal, right? To transduce this target recognition into measurable signal, we actually incorporated a redox, like push and pull nanoparticle film between the electrode and polymer. So in this case, if polymer bound to the target will fill the cavity. That will impede the access of sweat electrolyte to the redox molecule. Then in this case, your redox molecule signal will change. So by quantifying your redox molecule signal change, you can back calculate your target molecule concentration. So using this approach, we can realize continuous monitoring of every single type of essential amino acid, many different types of vitamin, lipids, and beyond, actually. So you may argue, well, you talk about scalable manufacturing using printing also, but now on your scalable manufacturing electrode, you need to coat your redox probe nanoparticle. You need to coat a polymer layer, so make the entire procedure feel like more complicated, right? How to simplify the process to enable truly scalable manufacturing. So we are presenting a new approach based on that mechanism. So we are proposing a cold shell nanoparticle in this case. You can through solution synthesize to make a lot of this nanoparticle in bulk, actually. This nanoparticle has a unique structure. It has a cubic core based on a push and pull analogs. In this case, we are using nickel HCF. This chemical compound gives us very stable redox signal. Even in biological fluid, you scan sarins and sarin cycles, they give you very stable signal. But push and pull is not. Push and pull, if you scan in a biological fluid, it will degrade over time. This redox signal gives us very stable signal already, this core. And this particle has also a shell based on molecule printed polymer. As I mentioned earlier, this MIP shell can work as a target recognition layer. So now the single nanoparticle has target recognition and signal transduction functionalities built in already. Through one-step printing, we can make this nanoparticle into ink. Through one-step printing, now you have your sensor ready already. It's very scalable and very generalizable. It can be applied to monitor metabolites, nutrients, and even therapeutic drugs. So I want to show you why we need to monitor drugs. So, in precision medicine, ideally, we should personalize the drug dose according to each patient because each patient responds different to different drug. And some drug, if you put too, like anti-cancer drug, for example, too high dose could have strong side effects, could possibly kill the patient. But you don't get enough, if you don't dose enough, you don't get effective treatment, right? That's why ideally for a drug, therapeutic drug, you want to keep the drug into therapeutic window, not too high, not too low. But for many drugs, this window is very narrow. It's very hard to control because the drug level in your body changes all the time, right? It's not practical now, even though now it's a standard practice. You come to the clinic, take blood draw, wait a few days to know the drug level at this moment in your body. You can imagine, quite complicated. So what if we can use a wearable sensor to remotely monitor drug non-invasively, and your physician will know your drug level? It's very important to realize drug dose personalization. So we developed using that sensing approach, a sensor that can monitor therapeutic drugs, including, in this case, anti-cancer drugs such as busulfan, mycophenolic acid, and cyclophosphamide. We have evaluated this in cancer patients. We observe very similar trend between sweat and blood, showing that we can use a wearable sensor to realize possibly the dose personalization. So I've showed you already how we can develop a sensor to look at metabolites, nutrients, many molecules, but most of these molecules, they are still at millimolar or micromolar level. But many clinically relevant biomarkers, they are actually proteins, hormones. Their concentration can be very low. Actually, it could be nanomolar, mostly even picomolar or lower. How we can realize picomolar level target analysis using a wearable sensor. So what's the difference for wearable analysis versus laboratory analysis? Many of you probably have done ELISA, laboratory biomarker analysis. You have your biomarker, you can, using your sample kit, you can do incubation, washing, then eventually use a plate reader or spectrometer to take the reading. You rely on equipment and still do a lot of benchtop operation to realize analysis. But for wearable sensor, we don't want that. We want the user wear the patch, direct take the reading, or click button from phone, then the measurement will be automatically conducted. That's why it's more challenging. So I want to show you two different approaches, how we propose to measure the picomolar level targets. Firstly, how to measure protein. And we picked a very important protein, C-reactive protein. It is one of the most well-known inflammatory biomarker. CRP, inflammation, firstly, is related to many leading cause of death, such as heart failure, such as COPD or COVID-19, sepsis, and so on. If we could do remote monitoring of inflammation remotely at home in high-risk population, this can be life-saving. But again, CRP concentration is very low. How we can detect CRP from skin non-invasively and automatically? So we propose a microfluidic salvage assay in this case. On our laser engraved graphene electrode, we can immobilize surface with a capture antibody. Antibody can recognize target, right? And we actually conjugate the detect antibody. Salvage assays, you have capture antibody, target, and secondary antibody to form this salvage structure. And our secondary antibody is actually conjugated onto a gold nanoparticle. One gold nanoparticle, you can conjugate many antibodies for signal amplification. You may not catch what I said, but I have a video to show you how they work. You have this wearable patch developed. Now, when you want to do the protein analysis, click a button from cell phone. Now, automatic iontophoresis will be conducted. A small current, as I said, will deliver drug molecules, stimulate localized sweat gland. Now, sweat will come out, enter microfluidics. CRP will bound to detect antibody. Now, continuous sweat flow will bring this reagent through the working electrode. Now, CRP bound to the capture antibody to form the salvage assay. Now, continuous sweat flow will rinse away additional excess amount of reagent, leaving clean sweat in the end. Eventually, we can do detection on the electrode. But what are we measuring? Because the antibody don't give us measurable signal. Initially, we actually conjugated a redox probe, thionin, on the surface of our detector antibody. ELISA, enzymatic ELISA, people conjugate enzyme here. But here, we are incorporated a redox molecule thionin, which give us unique measurable redox signal. Now we can quantify how much thionin signal on your electrode, then we know how much C-reactive protein in your body fluid. This approach is very unique because it gives us signal-on detection approach. Our general principle to realize high sensitivity is you want your background signal to be very low, close to zero ideally. Then even your target signal is very small, you can easily quantify changes because your background has low fluctuation, very low background, right? So using this approach, we can realize picomolar level protein analysis. And we have evaluated this in different populations, including healthy people, smokers, patients with COPD, patients with different type of heart failure, and patients with infection, and patients with just recovered from COVID-19. So we observed elevated C-reactive protein in sweat and in blood in patients with different health conditions. You see that. The correlation was pretty good between sweat and blood again. And you may argue, oh, how good is good, right? Look at this one. The dotted line is a healthy people CRP reference line. For patients with infection, severe infection, their CRP could change by even 10 times or even 100 times. Using this approach, we can say that we can possibly do non-invasive inflammation monitoring now using a wearable sensor at home. This can be very important for chronic disease management. This is how to detect a protein. It's a generalized approach. You can use this approach to detect the cytokines, for example, IL-6 or TNF-alpha. You can easily realize that. But how to detect a hormone? Hormone is different. If you do ELISA, you know that hormone analysis, people use a competitive assay. That's a signal-off approach. You have a high background, you measure signal decrease. That's very hard to do in situ in the body fluid because your background may fluctuate over time. So we present in this case a new approach, how to detect a small hormone molecule from a body fluid automatically. We also picked a very important hormone, in this case, female hormone estradiol. It is a very famous hormone already, play a very, very important role in women's health, estradiol level. In the fertility age, estradiol fluctuation will tell us ovulation window. give an early sign of ovulation, actually. It can be very important for IVF, for fertility control, and also not only for fertility management, but also for menopause. Women on average suffer 10 years from menopause, different health conditions, because their body cannot produce enough estradiol. That's why hormonal replacement therapy now is gaining more and more popularity, because you need to put a sensor patch, like hormone patch, or take the pill to increase the hormone level in your body. But now, no matter you're doing fertility or menopause, there's no good way for you to quantify hormone. There are no such at-home kit available yet. So-called at-home kit, you have to collect your blood or urine, you have to mail it out to a lab to do analysis. So we're thinking, oh, what if we can develop a wearable sensor that can non-invasively tell you female hormone information? So we present here a very interesting approach. It's the optimal sensor. We had designed the sensor to have two different interfaces. On the top, we call this interface biorecognition interface. It is inkjet printed gold nanoparticle electrode modified with aptamer. Aptamer is a nucleic acid, a single-strand DNA in this case, that can have specific bonding to a target molecule. So initially, this target molecule, the single-strand DNA, the aptamer molecule is bound to another single-strand DNA, and the single-strand DNA one side is linked with the methylene blue redox probe, loosely bonded, the couple. But now, if your body fluid contains estradiol, the aptamer will preferably bond to the estradiol now, because the competitive bonding. It will prefer bond to estradiol and so realize strand displacement reaction. Now the other single-strand DNA will be released from working electrode, because aptamer now prefer bond to estradiol. Now the single-strand DNA will be kicked off from this interface. Now it will diffuse to the nearby working electrode, which is essentially inkjet printed magazine gold nanoparticle electrode modified with a single-strand DNA with a complementary sequence. Now you have DNA hybridization happened at the working electrode. That means you have more methylene blue signal now on your working electrode. This approach is very interesting. If you don't have target in your body fluid, you get a nearly zero background. You don't have methylene blue on your working electrode. But even you have your small concentration target, now you can get a very small signal increase from a near zero background. You can still accurately quantify it. This is the way we can realize sub-picomolar level sensitivity automatically on the skin. And you may argue also, you're talking about this electrode release single-strand DNA diffuse to the working electrode in the microfluidics. What if you have a sweat flow in, flow out? It may rinse away your molecule already before you even reach working electrode, right? Our solution is we designed this capillary bursting valve. That when sweat come out, the sweat will start to enter the microfluidic reservoir, sensing reservoir. It will fill the sensing reservoir. But after the sensing reservoir gets filled, no sweat will flow into anymore. Because of capillary effect, sweat will flow out from another place. So we are sampling a fixed amount of sweat sample and doing the incubation and detection in the quiescent sweat matrix give us higher sensitivity and selectivity as well, accuracy in general. And you may also thought about, oh, what if people's sweat variation, sweat matrix kind of different, like may vary, right? To minimize that influence, we also incorporated in both work for protein and hormone analysis. We incorporated ionic strength sensor, pH sensor, and the skin temperature sensor to do the real-time sensor calibration so that you can get a more accurate reading. So now in our women subjects, we track them over 2 months, look at the menstrual cycle of hormone fluctuation. You see that sweat estradiol follow closely the blood one. And the correlation was pretty good as well. You can now, from the cell phone app, to real-time track the hormone concentration. Actually, last year, we also started a company, try to commercialize our wearable sweat sensor technology. The first target is actually women's health. We try to develop this female hormone tracker to non-invasively track female hormone. Most importantly is we start with IVF or fertility, later on can be used for menopause as well. So this is about hormone detection for women's health. And another very important topic, we always again, a lot of interest everywhere is stress monitoring. Because stress is so important, it's related to over 90% of diseases. Even stress is so important, stress is very hard to quantify. Right now, the gold standard is still based on questionnaires. So you can imagine the questionnaire can be very subjective. Now it's very hard to not only subjective. In many cases, it's very hard to implement. If a warfighter is performing task, you cannot say, oh, stop your work. Let me give you a questionnaire to evaluate your stress level. It's very hard to implement, right? That's why ideally we want to quantify stress level using a wearable sensor. Not only stress, this can be other different type of emotion, even pain, fatigue. Many these conditions are very hard to quantify. They're mostly based on subjective questionnaire. So we're looking at well-known stress biomarkers. Always everyone talk about the cortisol. So in this case, we designed a sensor patch. They can real-time monitor multiple stress hormones, not only cortisol, but also adrenaline, noradrenaline, 3 different types of stress hormone using a single patch. We designed the capillary bursting valve so that the sweat can enter and fill the first reservoir. After the first reservoir gets filled and analyzed, it will fill the second one to realize continuous sequential measurements, because we are using, in this case, antibody. Antibody, it's very hard to regenerate if they bound to a target. It's only one time used for 1 electrode. Our strategy is to combine this capillary bursting valve microfluidics to realize continuous monitoring. And very recently, with the development of the optimal sensor, we don't even need it to do this way. We can realize truly autonomous and continuous monitoring of the full day in general. So stress monitoring is one of the main topics we have been working on. We also, over time, formed a partnership with the US Navy, Army, and as well as US NASA, because everyone cares about the performance of their employees or performers. But again, people can still ask, even I know my cortisol level, I still don't know my stress level. So can you tell exactly how much stress I have, right? Those can be very important for performance as well. We even get a lot of reach out from US Olympic Games, and a lot of like NBA teams or the European soccer teams. They all care about the training, training performance of their players as well. So our solution is from beginning, as I mentioned, when we can collect now continuous biomolecular information, it's not previously accessible. When we do multimodal physical chemical data collection together, we get more comprehensive information about our health now. And with the help of AI, we can do a lot more things. We call biomarker discovery. In this case, one example is stress response assessment. So we designed a patch. They can simultaneously monitor 9 different types of biomarkers. This includes 3 physical biomarkers, 3 physical ones including skin temperature, galvanic skin response. This is the one used for commercial wearables to monitor stress. And we can monitor pulse waveform as well. So you can extract heart rate variability, and possibly blood pressure. And we also monitor 6 biomolecular markers. Among the 6 one of them, glucose. Many people may or may not know, glucose itself is such a good stress biomarker. You don't even need to take any sugar or food when you experience stress. For them, now I'm giving talk. My glucose level will be very high, actually. This is already very validated in a CGM. When you have stress, your cortisol level increase, your glucose level also increase very quickly. So we designed the sensor to be very stable. Now they can work in the biofluids for days without like a substantial sensor drift. Now during the day and night, across activity, you can collect the multimodal data. And we did also laboratory training, because when you do machine learning, you need to label the data, right? So we applied different type of stressors to our subjects. So let our subject to put a hand into ice water, then they will feel pain, of course, a lot of stress. Ask our subject to take VR game. When you do playing very intense VR game, you get very stressed out as well. Last but not least, when they do vigorous exercise, they will experience a lot of stress as well. We collect multimodal data. By using AI or machine learning, we can classify what type of stress they are experiencing and what is the anxiety or stress like a response outcome level. So here we show that we can predict a state anxiety level, one important part of stress response outcome. So this is just one example how multimodal data coupled with AI can be applied to many new applications. So I want to move on to an important part as well for wearables. I talked a lot of application already. And also, often people also ask, how do you power your wearables, right? I always say, mostly we are using a small lithium-ion rechargeable battery. So after it runs out of electricity, you can charge the battery, right? But again, not all the time, not everywhere. You have rechargeable electricity available. So we think a very important feature, now people talk about sustainability, how we can power future wearable more sustainably. One of the attractive way, if the wearable can harvest energy from the environment or from the human body, that could be a very important feature. So since we are doing sweat sensor, one of the first things we come into our mind is, what if we use sweat to power sweat sensor? Because sweat is wasted anyway, and sweat contains many important chemicals. Sweat contains, for example, lactic acid. It ranges from 5 to 60 millimolar, very high concentration. They are wasted already. What if we can convert the chemicals in sweat into electricity? In this case, we are developing a biofuel cell. Biofuel cell, they can lactic biofuel cell using lactic oxidase to catalyze the oxidation of lactic acid. Because lactic oxidation, the electron flow can be generated. So by using this biofuel cell, enzymatic catalyzed biofuel cell, we can get very high power. In this case, for the first time, we can realize a battery-free system, no any battery. And this system can do multiplex sensing, signal processing, and the Bluetooth wireless communication all in one. So how we can realize that with different type of nanomaterial, I will not go into detail, but the outcome is we can continuously get now up to 3.6 milliwatt per centimeter square power from human sweat, original human sweat. And even people's lactic acid level is low, you can still get 2 milliwatt level. If you work on low power electronic, you know, milliwatt level power is very high already. It's good enough for you to realize battery-free operation of many different type of tasks. And we can package our device, to a skin patch now, solely rely on power from sweat, not rely on any battery. You can continuously monitor ammonia, urea, glucose, pH, and temperature, and so on. Working with our IC design expert at Caltech, Professor Imami, she designed this IC chip, very small for power management. Together with our biofuel cell, the whole system is very tiny as well. So we also have a new chip that can simultaneously communicate with 15 to 20 sensor channels. So our future generation with wearables can be very small and low power. This is about biofuel. And we also come into like a discussion, what other source we can get power, right? Because biofuel cell, you still need rely on sweat to get power. So what if we can harvest energy from light? So at that time, our student, Jihong, when I talked with him about this idea, we mentioned that we don't want to just publish another paper of switching power source from biofuel to light. We want to build one of the ultimate or most comprehensive cell-powered wearable sweat sensor system. That means the system should be able to power iontophoresis, the way we use to induce sweat. They should be able to power ampermetric sensor, potentiometric sensor, voltammetric sensor, and impedance metric sensor, signal processing, and Bluetooth wireless communication, and not rely on California sunlight. We want to make sure it's working on the indoor, on the office light condition even, right? To make it more practical. So we eventually realized that by using a highly efficient provided gas solar cell, which has beautiful high power conversion coefficient on the weak indoor light. Strong sunlight is not very useful because who want to all the time stay on the California sunlight in the summer to get power, right? So eventually we realized all the goals using this highly efficient solar cell and low power electronics. And now during the day, across the day, in the morning to evening, we can continuously realize multimodal sensing using this battery-free system. And of course, you may argue, what if at night there's no any light, no strong light, right? This is to demonstrate that battery-free system can work. But again, in reality, we don't need to make it battery-free. We can always have tiny rechargeable battery. Now during the day, light power everything and charge the battery. During the night, battery power everything. We can show that for 4 to 5 months. You can rely on this to realize sustainable wearable operation without using any external electricity to charge your battery. So our lab, I talked a lot about sweat sensor already, but again, only 1/3 of my members work on sweat sensor. So we have many other topics going on. For example, we build a smart bandage that can be used to analyze chronic wound biomarker. Right now, chronic wound has attracted a lot of attention because it really causes a huge financial burden for US patients in general, for like diabetic ulcer. A large ratio of diabetic patients will develop diabetic ulcers, non-healing wound. So if we could know the wound condition better, we can, personalize or enhance wound treatment as well. So in this case, we developed a smart bandage. They can simultaneously track 6 wound biomarkers. They can tell us infection status and the inflammation status of the wound and even metabolic status of the wound. Not only they can track wound biomarkers, they can also deliver combination treatment. For example, they can deliver anti-inflammatory and antimicrobial drugs to treat inflammation and infection. And they can also do electrical stimulation to realize or facilitate tissue regeneration. So we have evaluated, packaged the entire system into a very small form factor. You see, we have evaluated this in a mice and rat model. And take one step further, we developed a microfluidic smart bandage this year also. They can harvest slowly secreted wound fluid. For real human patients, their wound fluid can be very little and slowly secreted. Too much wound fluid not good. That's why we need to sample it. And also, if new wound fluid mixed with old one, and you don't get a real-time information, and a lot of reactive species, their level will change. That's why ideally, we have this microfluidic system. They can suck out wound fluid from wound bed. They can transport, like our sweat sensor, fresh wound fluid through top of your sensor and get a real-time reactive species analysis. We did a reactive oxygen species, reactive nitrogen species analysis using this smart bandage in human patients with chronic wound and diabetic ulcers, chronic wounds such as diabetic ulcers and venous wound. And patients with wound, already we collect data, but how useful data is, right? Again, with the help of machine learning, we can predict now or classify the wound types or even predict the healing time. Wound type classification or healing time prediction right now, you have to rely on very experienced clinicians to do this. Imagine that for patients from rural area or people don't have even very good clinical resource, it's very hard for them to do that even. Now again, machine learning powered wearable sensor can play a very important role in this regard. So we also developed smart bandages. They can harvest Excel breast condensate. Our breast contain rich information. You may hear news here and there how useful the breast is. A lot of people work on gas sensors. But again, it's very hard to reach high selectivity using a single gas sensor. That's why people try to develop electronic nodes, put hundreds of sensors together, doing the mapping, machine learning, try to classify different conditions. But again, you need a really lot of data to train the model to make it practical. And we know that electrochemical sensor can reach high sensitivity and selectivity in the liquid phase. That's why here we are harvesting Excel breast condensate, EBC. Clinically, people already try to harvest EBC. In this case, you have the breast into a big condenser or ice cube to cool down your breast, harvest EBC, transport the EBC into a lab to do mass spec. But again, in this case, those are not practical because you have to rely on bulky equipment, and when during the transportation, a lot of reactive species level will be changed already. So our strategy is we develop a smart mask. The mask contains tandem cooling module, have 2 different cooling mechanisms. It has a hydrogel. The hydrogel will evaporate, cool down the temperature of the mask. And we also build like a mask based on using metamaterial. They can realize radiative cooling. By combining evaporative cooling and radiative cooling, no matter you are indoor, outdoor, with strong sunlight or without strong sunlight, you can cool down your breast by 7 to 14 degrees C instantaneously. Now you can harvest this EBC liquid. Using this bio-inspired microfluidics, we can realize pump-free transport. Fresh wound fluid will be transported into your sensor, get real-time analyzed. And after analyzed, the used EBC will be transported back into the hydrogel to refill water to the hydrogel so that the hydrogel will not dry. So this mask is, again, can work for a long time. From morning to evening, you can track different type of Excel breast biomarker from daily activity. We apply this to look at alcohol metabolism monitoring. You see EBC alcohol show very similar trend to blood alcohol. And we validated this against urea metabolism monitoring and airway inflammation monitoring in patients with COPD and asthma. And we even further validated this airway inflammation monitoring against the clinical standard phenol, showing this is very promising to realize airway inflammation monitoring. And recently, we also built a newer generation of this mask. They can last for days, up to a week, even a single mask with low cost. And the Gates Foundation give us a grant as well to make low-cost masks that we deploy to Africa in next year. So last example I want to talk is we can not only build a sensor that can attach to the skin, we can also build a sensor that you can swallow. They can collect data from inside your body. In this case, we build this ingestible pill so that their size is like very similar to the fish oil. You can swallow this, and this pill will go through the GI tract. We build different modality sensors that can track electrolyte, metabolites, and hormones such as serotonin and dopamine in your GI tract. It's very helpful to study brain-gut axis. And we have evaluated, this pill is very small, safe to go through large animal and human body. And we even did this in vivo test using this pill in the rabbit model. So to summarize my talk, I've showed you different type of body interface sensors already that continuously track information from the non-invasively accessible biofluids. And this large set of data can be very useful for a variety of biomedical applications. And again, a lot of things we don't know yet. If by collecting this data, multimodal physical-chemical data together with the AI, this can enable numerous new applications. And we think this will play a very important role in precision healthcare. In the end, I would like to thank my wonderful lab members that did most of the work and our collaborators for technology development and clinical validation. And last but not least, our funding support. Thank you very much for your attention.
Okay, it's open for questions.
Amazing talk. And I have two questions. The first one is for your sensors, how fast do they sample? Like what's the sampling rate of your sensors?
Depending on sensors, I would say most of them like metabolites and electrolyte sensors, those are instantaneously. We do very few seconds per point. Of course, they are really continuous. You can collect at even higher frequency, but we don't have to, right? I think related to the hormone protein, especially with neurodevelopment, if we some sensors only for 1 point, some sensor. Right now, we try to do most of the sensor continuous, semi-continuous. At least if you use optimal, probably several minutes per point. Yeah, I would say in general, ranging from sub-second to minutes level. Yeah.
I see. So my follow-up question is for your stress study. You said that you also incorporate the heart rate measurement, which seems to be from a PPG sensor.
It's a pulse waveform sensor, not a PPG. So we have this capacitive pressure sensor. You can really get a very detailed pulse waveform. Yeah.
And that I assume is supposed to be much faster than once every few seconds to capture.
Right. That sampling rate is much higher. Yeah.
Okay. Thank you.
Thank you.
Yeah, a great talk. I have two questions.
Yes.
The first one is for those absolute measurement, calibration is the key, right? Do you have to calibrate with each individual patient or person, or one calibration can fit all of the measurement you have? The second one is, this is the Photonic Institute, right? I want to know, looks like you solve a lot of those sensing problems. And I want to know whether there is still improvement in terms of sensitivity, whether photonics technology, like plasma, fluorescence, light time, and so on, can play a role that current your electrochemical sensor cannot solve.
Right, very good question. Firstly, related to the calibration, I would say from sensor point of view, many of the sensor we try not to do too much calibration. For example, those enzymatic sensor, we probably do one-time calibration of the batch. Already, we roughly know the performance. For the ion select sensor, probably also one-time calibration before you use the sensor. During the use, you don't need to do. But related to the wearable sensor, person, you may also need to do calibration depending on the application. For example, stress, or if I look at cortisol level, a different person, your baseline may be different. Some people, naturally, their cortisol is high. That's why for a lot of machine learning study, we normalize. We look at the trend. We look at how the rate of changes. So it really depends on the marker, how we analyze the data, right? That's part of the machine learning feature selection also. So for your next question, most of my sensors I showed today, they are electrochemical sensor. But in fact, optical sensor is very attractive. There are two different worlds, and both are very important part. we have now actually 4 or 5 postdocs working on optical sensor, not published yet, but I think optical sensor has a unique property. Firstly, in many of these target of markers, or like you have more choices of like how to label the data. And another very attractive part, we do some like wearable search, for example. You can truly do multiplexing in a small form factor. Right now for electrochemicals, each electrode I have to space it out to avoid interferences that can be very bulky. But optically, you can put many things with a similar tag or doing the search spectrometer to look at the response, I would say. Potentially, it can both reach high sensitivity and multiplexing in a small form factor. Yeah, that's something we are exploring. We have several people working on that direction. Yeah. Thank you.
Thank you for your talk. Sorry, back here. Have you tested your sensors with patients that have taken medications? Because I know that sometimes some medications can have some effects on your biomarkers. And if you have, how do you account for that bias?
Right. So there, we did 2 different kind of drug studies. Firstly, when I talk about the cancer drug personalization, right? In the clinical setting, we give the therapeutic drugs to the patient. We monitor their drug level change over time. This is direct measure drug. And secondly, we also did the drug influence of biomarker. For example, gout. A lot of gout patients, they take allopurinol. Like a diabetes patient take insulin to lower glucose level. Gout patient take allopurinol to lower uric acid level. So actually, this is a FDA regulated study. We did this in gout patients who underwent, to take allopurinol versus not taking allopurinol, how their uric acid level changes. We can study the dynamics in this way as well. We can clearly see that with drug, without drug, how their biomarker level changes. Yeah, in sweat, mirror what happened in the blood. Yeah. Thanks.
Hi, thank you for the talk. I just had a follow-up questions in related to drug monitoring as well. I was just wondering, what was the relationship, if you've observed, between the blood concentration, which is the current golden standard, versus the sweat concentration? Is it like a delay, or is it less prominent? And how reliable is the sweat concentration?
Right. So firstly, when you want to move invasive to non-invasive, we lost some accuracy, right? We'll not probably reach the same level accuracy as blood. But most of biomarker, we got a correlation between 0.8 to 0.9 something. It's pretty good already. And especially given you're doing continuous monitoring right now, as I said, it's not intended for real diagnosis. It's intended to look at the trend, look at people, how your biomarker behave over time, give people preventive care. In that case, this continuous monitoring coupled with this correlation, we think it's pretty promising for many applications already. But of course, there is delay. Even think about CGM, people do industrial fluid glucose monitoring, there is already 7 minutes delay. And what we see, depending on biomarker, the delay could be from minutes to like over 10 to 20 minutes, also around this range, the delay. But for most applications, this is already pretty good. Yeah. Thanks.
Thank you so much, Dr. Gao. This is so exciting.
Thanks.
So can you talk more about like how this biosensor can be approved by FDA, and in which aspect? Is it going to be used as a measurement device, or is it going to be able to provide clinically reliable information that doctor can use them towards precision medicine?
Right, that's a very good point. Because when we do a startup company, we always get this question, right? Like even different investors have different views about, do you want a consumer, or do you want to really like make a medical decision? So I would say both can be very interesting. Even like when we try to do one thing, even some program manager want, oh, no, we want to consumer, want everyone have access. For them, even female hormone, do you want to use it in the IVF clinic for ovulation induction versus a female want to increase the chance to get a baby? So both can be in parallel. And at least in my in a startup wise, we're looking at both options. There might be usually it's a fast pace to just getting data, not making medical decision. As the data is make meaningful changes already, this can be very informative, like Fitbit, before they get any FDA advice. But when we reach enough clinical data to prove its accuracy, and we believe those medical decisions can be very beneficial, especially one of the first market we're looking at, even IVF, is that part we really want can be used for ovulation induction assistance. Yeah. But right, because without too much clinical data validation, we cannot get class 2 classification like clearance anyway. So it could be a fast pace to getting direct to consumer product, only passively collecting data. That's what a lot of medical device company start with. Get approval to get data. Then when I get enough accuracy, we want to make a medical advice or decision. Then there's a longer pace. Yeah. Thank you.
Yeah, I just want to follow up. I saw you have a lot of data with a human.
Yes.
Do you get IRB protocol for all of the study?
Yes.
Uh-huh.
And we have like 10 to 15 at Caltech, also 10 plus in different medical centers for IRB protocols. Yeah.
That's great. Any other questions from you guys? Oh, I can probably ask the last question. You have published so many high-profile papers, and just give us some secret. How do you get there?
I would say, at least when we start a project, I always ask students, what is the gap of this field? At least you need to convince the general person may or may not be the expert in this field. So what is the gap? Why other people cannot do it? Why we are the right person to? Why is this a technology? If you say nobody thought about this, that's hard. As an engineer, people thought about it. But what are the technical challenges? What breakthrough? What a big, like medical needs? There are many medical needs. We pick important problem and we see what are the technical gap and how we bridge the gap. Maybe through innovation A, innovation B, or combined version. So when we really always think about because we are biomedical engineer, we try to solve the biomedical problem. When we focus on big problem, addressing the technical, the real gap in the field, maybe not fully addressing, we are just halfway through, very likely also, even we want to fully address, they will still lead to very impactful or meaningful outcome. Maybe we are not the person who fully address the problem, but we can give people inspiration how to address or how to improve or make the gap smaller. So those are the things we always think about: tackle big problem and make it clear what are the technical gaps and how to develop a solution to bridge this important problem. Yeah. Then in that case, I feel for general public or for even general editors, they'll be convinced, oh, this is a very important problem. Then they think about the way you sell the papers, like how I address. When people see the gaps you're talking about, people also agree, and people also realize you are really addressing or partially addressing the gaps. Naturally, it has high impact, I feel.
That makes sense. Sorry, I forgot. Do you have any questions from Zoom audience? I saw Abby there. Faye, do you guys have any questions? Or Yoda also, do you have any questions?
Nope.
Okay. Sounds great. Thank you all,
Good.
and thank you, Dr. Gao.
Thank you.
Very impressive.